Hello and welcome to the Joule-Thomson channel, and this video is about an isenthalpic expansion in a pressure enthalpy diagram. The discussion is based on an example, which is as follows. A continuous stream of saturated liquid Freon 1 to 4 at the pressure of 1 megapascal passes through a valve that has perfect thermal insulation. The pressure of the Freon 1 to 4 stream that exits the valve is equal to 0.1 megapascal. Knowing that the operation is at steady state and neglecting any change to the kinetic and potential energies, use the pressure enthalpy diagram of Freon 1 to 4 to find the fluid's temperature in the input stream to the valve and quality and temperature in the output stream from the valve. Let's apply the mass and energy balances to this problem, beginning with the mass balance. The left-hand side of the mass balance is the time derivative of the mass inside the system. The right-hand side accounts for the contributions of the input and output streams. However, the operation is at steady state and therefore the time derivative on the left-hand side is equal to 0. And there is only one input and one output stream to the valve, and therefore we obtain equation number 2, meaning that the flow rates in and out are the same. We now proceed to examine the energy balance. On the left-hand side, we have the time variation of the energy in the system, and on the right-hand side, the effect of the input streams, output streams, expansion, contraction of the system, heat transfer rate, and shaft power. As we're dealing with a steady state, the time derivatives on the left-hand side and on the right-hand side vanish. In addition, the valve has perfect thermal insulation, and thus the heat transfer rate is equal to 0, and there is no shaft power. Finally, we use the information that changes to the kinetic and potential energies are negligible, and by taking all these into account, we find that the enthalpy of the input and output streams are equal. Combining these results with the outcome of the mass balance, we finally find that the specific enthalpies of the input and output streams should be the same. We call this an isenthalpic process. Other names are throttling process, Joule-Kelvin expansion, and Joule-Thomson expansion. This is the pressure enthalpy diagram of Freon 1 to 4, and we thank the Chemours company for granting permission to use it. We start the graphical solution by locating the point that corresponds to the input stream. It's a saturated liquid and should be on top of the saturated liquid line at the pressure of 1 megapascal. This condition is represented by the red dot on the diagram. Freon 1 to 4 undergoes an isenthalpic expansion, and an isenthalpic line in the pressure enthalpy diagram is a vertical line. Because it's an expansion, the pressure should drop, therefore we go downwards along the vertical isenthalpic line, ending at the pressure of 0.1 megapascal. This condition is represented by the purple dot on the diagram. By now we have located the conditions of the input and output streams, and all we have to do is to collect the information regarding their properties. For the input stream, we see that the temperature is 60 degrees Celsius. For the output stream, the quality is 0.5, and the temperature is slightly below minus 10 degrees Celsius, roughly minus 12 degrees Celsius. In summary, we find that the temperature in the input stream is about 60 degrees Celsius. The quality after the valve is 0.5, meaning that 50% of the mass is in the vapor phase, and the temperature of the output stream from the valve is equal to minus 12 degrees Celsius. Because such a temperature drop is achieved, this type of process is commonly used in air conditioners and home refrigerators. Thank you very much for viewing this video, and if you have any question or comment, don't hesitate to contact us at the Joule-Thomson channel.